All right, so we are now into chapter 11, section 11.1. We're going to start talking about the idea of sequences. um, in general, a sequence is actually pretty easy to define. A sequence is simply a list. Easiest way to say that. Typically, the list has some kind of a definitive order to it. Um, does not have to be numerical, although for the most part, what we're going to be dealing with is numerical. You could certainly have a list of, I don't know, months of the year, January, February, and so on, whatever. It just has to be a definitive list of some kind with a given order. Given that fact, we are going to label the elements of that list as A1, A2, A3, and then so on all the way up until you get to the nth term of the list. The subscript represents the number of the term of the list that we're talking about. And then if you have an infinite list, then you'll have a dot, dot, dot at the end because past the nth term, it's just going to keep on going. So there will be a lot of notational issues that we're going to have to deal with in this specific chapter, but hopefully most of those are something that you are already familiar with. All right. Since we are going to be pretty much exclusively dealing with infinite sequences once we move into the latter parts of the chapter, it's going to follow that there's always going to be a next term in the sequence. And the next term, if the current term is the a sub n term, the next term would be the a sub n plus 1 term. The term after that would be the a sub n plus 2 term, and so on. It just helps us to define these things so that we know what's going on as we start to deal with the notation. So a sequence can be written in several different ways. We'll talk about a few of them just so you have an idea if you see these things, what they are, and that they all pretty much mean the same thing. In letter A here, sequence, kind of with that brace notation there of n over n plus 1. And then you see it's got n equals 1 and infinity on the outside to the right of the brace. N equals 1 just pretty much tells you, okay, you're going to start with your first term, and then it's going to go up to an infinite number of terms. Another way to write your a sub n or your general notation for your sequence is without the brace notation, and it's just understood that it would be n over, excuse me, n plus 1. It just means that that is going to be the defining term for every term in the sequence. In other words, you can plug in any n value you want to, starting with 1, or wherever the sequence happens to start. Typically, if it's unlabeled, it starts at 1. And then you'll be able to figure out what term it is. Another way to define a sequence is to actually start listing the terms of the sequence. So for example, in this one, if we start with n equals 1, substituting 1 in for n, you would get 1 over 1 plus 1, which is 1/2. Then if you go with n equals 2, you would get 2/3. N equals 3, you would get 3/4. N equals 4, we would get 4/5. And obviously this is infinite, so at some point you pretty much just have to go dot, dot, dot. And then a lot of times you want to list the nth term, if it's possible, in there. And then you would indicate another dot, 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 which just means that it goes on forever after that. Sometimes these braces are not going to allow me to write all that stuff out, but that's the idea. So you could see it like that. So you would be given a certain number of terms, a defining term. Sometimes you're just given a certain few first terms, no defining term, and you would actually have to figure out what that is. We will deal with that as well. So in the second one, letter B, we have this sequence of terms. It's -1 to the n power times n plus 1 all over 3 to the n. So again, we can take all that stuff in the brace and just write it out here without the brace. Okay, and that is an acceptable way to write the sequence. That's the nth term of the sequence. Again, you could do this by substituting in values for n and writing out the terms. So if we start with n equals 1, plugging in n equals 1, the -1 to the first power would give you a negative, and then you would substitute n equals 1 into the n plus 1 and 3 to the n. So what you would get is -2/3. The second term, if you plug in 2 for n, well, now you've got -1 raised to the second power, which makes it +1. Plugging in 2 into everything else would give you 3/9. Yes, I am aware that that reduces to 1/3. I'm going to leave it as 3/9 for now, but you could reduce it. Plugging in n equals 3. Once again, now your term is going to be negative because you're going to have an odd power of -1, would give you -4/27. Plugging in 4, it's an even power, so it's going to make it positive. We'll make it 5/8, and so on. The reason that I showed this one in particular is because of that -1 being raised to the n power. What that does is that gives you alternating terms. So you can see that every other term in this is going to have a positive and negative value. That's going to become pretty common. We're going to see that a lot. Okay. Letter C, the reason that I put this one on there, notice that in the brace there, it's got the square root of n minus 3. But what you should also notice is that n has an equal sign, but nothing after it. That was actually not a typo in this case. That's actually meant to be there because we cannot start at n equals 1. It does not make any sense. You would get the square root of -2. It's not a real number. So we're not going to start there. You would actually have to start at n equals 3, because 3 minus 3 being 0, it's the smallest square root in real numbers that we're going to be able to use here. So that is why that one was left blank, just to make sure everybody realizes you actually have to start with a number that makes sense. So then after that, we can just write this as square root of n minus 3, and then once again, start plugging in numbers. So this isn't too hard. If you plug in 3, you'd get 0. Plug in 4, you get 1. Plug in 5, you'd get square root of 2. Plug in 6, you'd get square root of 3. Plug in 7, you would actually get 4, but I'm just going to stop it there and go ... But that would be your sequence of terms. And then in the last one, letter D, again, there's a reason that n was left blank. This one does not technically have to start with n equals 1. It could actually start with n equals 0. And the reason for that is because cosine of 0 makes sense, especially when you're talking about if you're using a unit circle or 0 as an angle or whatever, because if you plug 0 in for n, you would get cosine of 0. Well, that would be 1, so that would actually be our first term over here. I'll finish that off in a second. Otherwise, I'm just going to write this as cosine of n pi over 6 as our general term. And then again, so we've now plugged in 0 and gotten 1. Plug in 1, you would get cosine of pi 6, which is √3/2. Plug in 2 for n. 2/6 reduces to 1/3, so you're going to get cosine of pi thirds, which is 1/2. And then if you plug in 3, you're going to get cosine of pi halves, which is 0. And then I'll just do one more. If you plug in 4, you're going to get cosine of 2 pi over 3, which is -1/2. So what you can see is that the signs do start changing here, but they are not alternating in any fashion. And then you could basically just keep following that stuff around. You'd get all these unit circle values, and it would have a continuing pattern. As a matter of fact, eventually, this, as you know, this pattern will repeat. All right, so that's just kind of the idea on how you find terms of a sequence or how to write a sequence and so on. Our first real example here says that we want to find a formula for the general term of a sub n of the given sequence. Now, I do have to note that on here, I don't know whether it's this way on your paper. I don't remember if I fixed it, but on here I have a correction to make. That last term that's in there is the -7/3125. Actually should be positive. That was a typo, and I just haven't fixed it for some reason. That should be a positive value. All right, so what you should see is that your first term is positive, second one is negative, third is positive, fourth is negative, fifth is positive. It's alternating. Okay, that's important because that's going to be an important part of what you notice when it comes to writing a general term. Now, the way I like to do this, and there are different ways to do it, the way I like to do it is I like to break it up into potentially 3 different components. 1, do I have alternating signs, which we just determined that we do. So the first thing is we're going to write the general term of the sequence. We've got to label that a sub n. Since I have an alternating term, I know what I'm going to have out front is a -1 raised to some power. For right now, I'm just going to put n, and then we'll see if that actually works. If not, we'll actually fix it in a second. Then I'm going to look at the pattern in the numerator and the pattern in the denominator separately. I'm actually not going to try and look at this as one whole fraction. I think it's harder to do it that way. If you can, by all means, go ahead and do so, but I think this is the easier way. What you should notice in the numerator is that it is increasing by 1. So it is a linear function, right? Something which increases by the same amount has a common slope, which means it is a linear function. So when we write this, it should be basically in some kind of a form of y equals mx plus b without the y equals part. It's just going to be an mx plus b type form. So the question is, what is the m? What is the slope? Well, it's increasing by 1. Instead of using x, we're going to use n as our independent variable. So it would be like saying 1n. But if I just leave it as 1n and I plug in, because this would be my first term right here, this would be my second term, third term, fourth term, and so on. If I plug in 1 for n on the numerator, I'm going to get 1 times 1, which is 1. That's not right. It needs to be 3. So what do I need to do to get from 1 to 3? Well, I need to add 2 to it. Basically, that's like your y-intercept portion. So it's really just 1n plus 2, or you could just write it as n plus 2. And then if you plug in any of the other values, the 1, 2, 3, 4, you should get the correct numerator. The denominator looks to be like we are multiplying by 5 each time to get the next denominator. When you multiply by something, that means that is your common base, which means it's going to be 5 raised to an exponent. It's going to be an exponential function. So we're going to have 5 raised to the n power. And again, we'll adjust it if it's not exactly n, but it looks like it is. Because if I plug in 1, I get 5. If I plug in 2, I get 25. If I plug in 3, 5 to the third power is 125, and so on. So all that looks good. The only thing I have to go back and check now is, did that -1 part work? Well, if I let n equal 1, and I plug 1 into here, I'm going to get -1 raised to the first power, which is negative. But my first term here is positive. So this is not exactly the right exponent. What I need to do is I need to go ahead and add 1 to my exponent, because now if I plug in 1, the exponent becomes 2, which means -1 squared is a positive number. So it makes that first term positive. And then when I plug in the next number, it'll become odd, which will make it negative, and so on. So if you're backwards when you plug in n originally, just add 1 to it, and then you're going to make it the right way. All right. There are going to be some other patterns that we're going to hopefully be able to pick up on as we go through the rest of the chapter, certain things to look for and certain types of functions that are going to be the most commonly used. But you will have to be able to take a given sequence just by the terms and write the general term of the sequence, which is what we did there. All right. There are some sequences which are very commonly used in mathematics and sciences, but the pattern is not so easy to figure out. Now, I threw one on here that is not easy to figure out. If you want to try it before I start telling you what it is, pause it and try and figure it out, but this is not an easy one. Because if you look at 7, 1, 8, 2, 8, 1, and so on, it's not a mathematical pattern like you do something to one term to get to the next term. That's not the way this one works. But it is a sequence. And what this represents the nth decimal place. Well, we learned if I can write correctly, of the number e. And for those of you guys who aren't as familiar, e is approximately 2.71828182845, and so on. It just keeps on going. E is one of those numbers very much like pi, that there is no discernible pattern to the decimals. It is an irrational number. Now, if I had put 14159, a lot of people probably would have picked up on that. Oh, those are just the decimal places after the 3 for pi. So I just didn't want it to be quite as obvious. So that's what this is. This defines, I should put the out from here, the nth decimal place of E. Okay, and then we also have this one, which is probably even more common down here. This is a very common type of thing. So what it tells us is that f of 1 is 1. Let's write that in there. F of 2 is 1. Okay, great. And then it says that f of n is going to be defined by taking f of n minus 1 and f of n minus 2 and adding them together. Or basically, a way of saying that is your current term is going to be done by taking the previous term and its previous term, or basically your previous two terms, and adding them together. And that starts with n equals 3 and greater. So to get the third term, I'm going to take 1 and 1 and add them together, and I would get 2. To get my fourth term, I'm going to take my previous two terms, which are the second and third terms, 1 and 2, and add them together and get 3. And then I'm going to take 2 and 3 and add them together and get 5. And then 3 and 5 will get 8. 5 and 8 will get 13, and so on. And some of you may already have recognized what this is. Again, it is a very, very common sequence. It actually is a very interesting one in the fact that this actually occurs in nature all over the place. If you don't believe me, look it up. It's very interesting. This is known as the Fibonacci sequence. And I should probably change that to a capital F out of respect because this is a person's name, Fibonacci sequence. Again, very common sequence. Not really something that we will deal with so much in this video or in these videos, but this is a very common one. All right. So a sequence can often be represented graphically, either on a number line or by plotting its graph. So what we're going to do is we're going to take a look at an example that we've already seen, the n over n plus 1. And we're going to remember that the domain of a sequence is the set of whole numbers because you can't have a negative second term of a sequence. That doesn't make sense. We can have a 0th term, we can have a first term, second term, third term, and so on. 0th term typically, by the way, means a starting, like an initial starting point, initial condition kind of a thing. So let's write down over here, we'll put 0. Let's see if we can start writing the terms out. So the first term that we had 1/2. When we plugged in 1, we get 1/2. We'll put a half right here. The next one we had was 2/3. So I'm just going to, for the sake of it, that was 1/2, so 1 is about right here. For the sake of it, trying to figure out exactly where all these pieces are going to go. Might be easier to put a 1 out there. So 2/3 is going to be 2/3 of the way up, maybe right there. 3/4, that's going to be halfway in between the half and the 1. 4/5, maybe right about here. 5/6, and so on. I'm not going to be able to keep writing the numbers in here. What you should notice is that all of these little dash marks should start getting closer and closer together. But one of the other things you should also notice is they're going to start getting close to, but they're never going to get to 1. Okay, so the dash marks that I'm putting in there are going to get closer and closer together, but they're also never going to get to 1. Again, an important concept for what's coming up. All right. You could also represent it. That might not be the easiest way to see it, but hopefully that makes sense to some people. If not, maybe this one won't make sense. We could also do the graph like this. So here's 1 at the top. I'm going to go ahead and throw an asymptote on there because you're going to see what happens here. So as we do our terms, this will be the first term, second term, third term, fourth, fifth, sixth, seventh, and so on. I'm not going to plot all those, but the first one we said was a half, which would be right about there. The second one was 2/3, maybe right about there. The next one was 3/4, right about there. 5/6, and what you should see as we go on and on and on is that these things are going to get closer and closer and closer to 1. So from either graph, doesn't matter which one it is, it appears that the terms of the sequence are approaching the value of 1 as n becomes large. Okay, and this is going to take us all the way back to calculus 1 with limits. All right. So we can actually show that that was actually the case if we take 1 minus, because 1 was our predicted limit there, 1 minus the n over n plus 1, what we get is an actual remainder of 1 over n plus 1. Okay, that's just basic algebra, but I'll show it. So if we make 1 a common denominator of n plus 1, that would be n plus 1 over n plus 1. Okay, that's our 1 minus n over n plus 1. Well, then if you subtract those things, the n's on the top would go away, and all you're left with is 1 over n plus 1. So that's kind of how you get that, just to make sure everybody can see that. So what we can show, that's your remainder. That's the difference between 1 and our terms of the sequence. Well, we can actually show that that difference can be made extremely small if we let n get really, really big just using limits, the idea behind the limit. So the limit as n goes to infinity of n over n plus 1, we know to be 1. Okay, that's way back to limits. Hopefully that's not something that comes as a surprise to anybody. You can basically use the growth rate property there, that the numerator and denominator have the same growth rate, so you can divide the leading coefficients to get your limit. In general, if the limit of the terms of a sequence approach a finite number, then we're going to call that limit capital L. That's just the label we're going to give it. Okay, this is the important part about this, and then we'll come back with a second video to start doing some examples. A sequence, a sub n, has a limit L, and we're going to write it in one of the following notations. Probably going to use the one on the left. Don't even worry about the ones on the right for right now. I won't use those. The limit as n goes to infinity of a sub n equals L, whatever the limit is that we come up with. If we can make the terms of a sub n as close to L as we like by taking n sufficiently large, in other words, let n approach infinity of our sequence and see what we get. If we get a finite number, if we get an actual limit that doesn't say infinity or something like that, and we just get a number, then the limit exists. And if the limit exists, we call the sequence convergent, or we say the sequence converges. Converging meaning going towards, converging onto something. So it means you're getting closer to. Otherwise, if that doesn't happen, then we call the sequence divergent. I cannot stress to you how important this overall concept is going to be for this chapter, the idea of convergence and divergence. So again, the general concept, the convergence of something as something gets closer and closer to, approaches, however you want to say it, it converges to that thing. Otherwise, it diverges, goes away from, does not converge to. Maybe is the easiest way to say it. So again, if you take the limit as n goes to infinity of your sequence and you get any finite value, an actual finite number, then it is convergent. Otherwise, it is divergent. All right, a note just for the future is that all the same limit laws that we've used before are going to apply here, as well as the squeeze theorem, which we will be using at some point in time during these examples. And then there's this theorem, which says, if the limit as n goes to infinity of the absolute value of the terms of the sequence a sub n equals 0, then the limit as n goes to infinity of that sequence is 0. Okay, that's going to be an important theorem to be used as part of one of our proofs and one of our examples. But basically it just says that if you take away the fact that a sequence could alternate in sign at some point in time and that limit approaches 0, then the limit of the whole sequence approaches 0. It doesn't matter that there's an alternating sign in there or not. And then the last thing is, while L'Hopital's rule cannot be used for sequences, We can still kind of get away with using L'Hopital's rule, because what we can do is we can define the nth term of the sequence as a function of x, and then apply L'Hopital's rule here to be able to help us figure out the actual limit if necessary. All right, that is going to be all we're going to do for this particular video. We will come back with another video and start our examples.